the greatest of human endeavors is a risky business.
Houston, we've had a problem here.
NASA led the world into the exploration of space, but behind the scenes, out of the public eye, mistakes, mishaps, and failures plague the space industry.
Obviously a major malfunction.
Discover how NASA space failures further exploration.
Landing gear down and locked. Having fired the imagination of a generation, a ship like no other, its place in history secured, the space shuttle pulls into port for the last time. Its voyage at an end.
The Space Shuttle program ended in 2011 after 133 successful missions.
Mission complete, Houston. After serving the world for over 30 years, the space shuttle's earned its place in history and it's come to a final stop.
When the first space shuttle launched in 1981, the program was the most groundbreaking, ambitious space exploration effort in human history. The science fiction concept of regular treks to and from space had suddenly become reality. At the height of the program, the space shuttles were flying 3 to 8 missions per year, constructing the International Space Station, maintaining orbital telescopes like Hubble, and enabling groundbreaking scientific research and discoveries that changed the way humans lived on Earth. But with literally millions of parts to this amazing flying machine, and a labor force of up to 7,000, the scope and complexity of America's space transportation system made mistakes almost inevitable. There were simply too many people and too many variables to expect nothing would go wrong, and on occasion, it did. Most space mistakes are caused by human error, a miscalculation, an oversight, a failure to call for an investigation when something doesn't look right, or even someone trying to do something good not realizing how it affects the entire system. A critical oversight left NASA's solid rocket boosters literally hanging by a thread and put unsuspecting civilians directly in the crosshairs of more than 1 million pounds of the most explosive rocket fuel on the planet. But first, because a material supplier was just trying to help, an astronaut's life is put in danger during a harrowing training exercise. The orbiter is the part of the full space shuttle that operates in space and returns to Earth. It is equipped with what is called an emergency egress slide. The slide is similar to the escape slides used on commercial aircraft, which have saved many lives. The orbiter's egress slide could be used in a transoceanic abort landing, a scenario which would force the shuttle launch to be aborted and the orbiter to land in the ocean, a critically dangerous scenario that would only play out if something went horribly wrong during launch. The slide could also be used in an emergency landing situation when the orbiter returns from space. During entry, descent, and landing, or EDL, the orbiter becomes a glider. The entire 5,000-mile flight through the atmosphere, starting at supersonic speeds of 17,000 miles per hour, is unpowered, with only restricted directional control available to the pilot. A series of banking maneuvers along with atmospheric resistance are used to slow the orbiter as it approaches for landing. With no engines, the orbiter has no ability to make a second landing attempt if something goes wrong. It cannot circle around for another attempt like a typical airplane. It has one chance to get it right. An obstruction on the runway or a mistimed or misaligned approach could result in the orbiter landing in a Florida swamp. The emergency egress slide was designed for just such a scenario. Although the slide was never needed during the history of the Space Shuttle program, learning to deploy and use the slide was a critical part of each astronaut's training regime. One training exercise went terribly wrong. Astronauts are assigned to missions based on experience or expertise in science or spaceflight, depending on mission objectives. Training for an assigned mission can take up to 3 months, while planning for that mission can take years. Astronauts' lives and health are tightly controlled during the intensive training phase. As launch day approaches, if an astronaut becomes injured or gets ill, the entire mission can be delayed, which can cost millions of dollars, and in some cases, narrow windows of success can be lost, such as repair missions to the Hubble Space Telescope. So once training begins, astronauts are closely monitored and protected. While training with the emergency escape slide, astronauts wear full flight suits, and before they can be cleared for launch, they must be able to fully deploy the slide and exit the orbiter in under 7 minutes.
Atlantis Houston, MS3 Comcheck. Tab release. Visor.
As they descend the rubber inflatable slide, a carefully calibrated strip of coarse material slows the astronauts so they are not injured by descending too fast. This strip is called the deceleration strip. A decorated female commander and 2 other male crew members were training for an upcoming mission. The first 2 crew members exited the vehicle and noticed that their descent was slower than usual. But in the urgency of the training exercise, there was no time to stop the commander from descending the slide. And when she did, her mission and NASA career almost came to a tragic end. A routine training mission quickly turns into a life-threatening situation as astronauts practice deployment and use of the orbiter's emergency egress slide. After deployment of the slide, heavier crew members notice their descent is slower than normal. When the lightest crew member descends, she stops suddenly when she makes contact with the slide's deceleration strip. The sudden stop causes her to lose balance, and she nearly tumbles down the slide. Such a tumble in a full flight suit could have resulted in life-threatening injury. This also could have seriously delayed the mission, costing millions of dollars. The astronaut is carefully assisted off the slide. Training exercises are suspended, and an investigation is immediately launched. The deceleration strip is analyzed. Testing reveals that the material is 3 times coarser than it is supposed to be.
During the development of the requirements to procure this particular item, there is an expectation that those products will be delivered to us as we expect them to be.
In disbelief, NASA contacts the supplier of the slides, and a grave concern emerges. Are the slides currently installed in the actual orbiters wrong as well?
We design and we train and we provide equipment that is destined to go into the harshest environments of space. And our first priority on this is to make sure it's done safely.
Is the health and safety of the astronauts in jeopardy from the very device designed to protect them? NASA needed answers, and fast. The investigation confirms that NASA had ordered 6 new egress slides to replace slides that had been in operation for 10 years.
When we're procuring an item from industry, we go into extreme details on creating the contract. And within the contract to this vendor, requirements are established, processes are established, and the criticality of the product is communicated to the contractor.
The slide with the wrong deceleration strip was one of the new slides, and 2 of the other new slides had already been installed in Columbia and Endeavour. While talking with the primary company that manufactures the slide, NASA discovers that a second company that supplied the rubber-coated nylon deceleration strip also supplies the same material to a military customer. The material is used in a classified military application to evacuate troops from an area quickly. The military customer, who bought much more of the material than NASA, asked the company to make the material rougher to help soldiers evacuate easier. They changed the material but failed to modify the material part number. When the Space Shuttle program ordered new slides, the new, rougher material was provided for the deceleration strips. The primary company that puts the slide together checked the part number, but did not test the deceleration strip when it was delivered. They assumed the material was correct based on the part number. The slide was assembled and delivered to NASA.
Any deviation or any change of those processes need to be communicated back to the customer. And whether the company thought it was insignificant or not, based upon how we're using this material, it should have been communicated back to us.
The company that supplied the deceleration strip material thought that changing the material was a good thing to protect the lives of United States troops. But because the change was not reported to NASA, it jeopardized the life and health of an astronaut and a space shuttle mission.
Processes are established for one result, and that is a safe and successful mission.
Fortunately, the deceleration strips were all replaced with little effect on mission schedules. As NASA builds the next generation of spacecraft and sets its sights on Mars, the space agency is working to ensure this kind of space mistake never happens again.
Process is a process no matter which program is being worked on, and the change impacts still have to be understood and analyzed so that we can pass on from one program to another, because ultimately we're all going to space.
Next, A critical oversight leaves NASA's solid rocket boosters hanging by a thread, a costly space mistake that put unsuspecting civilians directly in the crosshairs of more than 1 million pounds of the most explosive rocket fuel on the planet. NASA learns from their mistakes.
Houston, we've had a problem.
And NASA works hard to catch mistakes before it's too late. Space Shuttle program lessons are still being applied to today's new spacecraft. The Space Shuttle was comprised of 4 primary components. The orbiter, where the Space Shuttle is piloted and from which the astronauts live and work. The Space Shuttle main engines, or SSME, which are housed in the aft section of the orbiter and provide directional control during launch and descent. The external tank, which supplies the liquid hydrogen and liquid oxygen to the Space Shuttle main engines. Finally, the solid rocket boosters, or SRBs. The SRBs together provide the 6 million pounds of thrust needed to launch the Space Shuttle and escape Earth's gravity. The SRBs arrive at Kennedy Space Center in 4 sections, each weighing 325,000 pounds. The sections are transported from Utah across the nation by rail. The very earliest rockets were solid fuel rockets powered by gunpowder. Invented by the Chinese in the 13th century, they became weapons of war for the Chinese, Indians, Mongols, and Persians. Intercontinental ballistic missiles, like America's Minuteman and Peacekeeper, Russia's Topol, China's Dongfeng, and India's Agni 5, all utilize solid fuel because they can be stored for long periods of time and can launch on short notice. When the Space Shuttle launches, the Space Shuttle main engines are activated first. Then the SRBs are ignited. Once ignited, they cannot be turned off or stopped. Within seconds, the shuttle clears the launch pad. The power of the SRBs force the Space Shuttle through the resistance of the atmosphere and out of the grasp of gravity. As it ascends, the Space Shuttle travels faster and faster while gravity becomes less and less. The SRBs have a short but powerful life. They burn out and are jettisoned just 2 minutes after liftoff. The Space Shuttle main engines spend the remainder of liquid fuel from the external tank to reach orbit. The spent SRBs plunge harmlessly into the Atlantic Ocean, some 150 miles downrange. Days before launch, NASA dispatches 2 retrieval ships, 1 for each booster. The ships wait in a safety zone near the projected splashdown location.
There it is, straight out.
They retrieve the spent boosters. And tow them back to Kennedy Space Center. The booster casings will be refurbished and used again. When the solid rocket booster's 6 million pounds of power is controlled and directed to reaching orbit, it is an incredible feat of human engineering. The Challenger disaster of 1986 is a painful reminder of the violence and destruction that happens when that power becomes uncontrolled. A seal between 2 rocket motor segments was damaged by ice before launch. 73 seconds into flight, gas from the burning solid fuel erupted through the seal.
Challenger, go at throttle up. Challenger, go at throttle up. 1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
And within seconds, the entire rocket was torn apart. The first explosion initiated a series of events that led to the explosion of the liquid fuels in the external tank. None of the crew survived.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Due in part to the volatile nature of solid rocket fuels, the Space Shuttle's SRBs were manufactured and refurbished at an isolated facility in the deserts of northern Utah. The facility is just miles away from the Golden Spike National Monument, where the East and West were joined by the Transcontinental Railroad in 1869. The final Golden Spike linked the United States together. Trains were the new technology of the day and were transforming the world, opening new commercial opportunities and the freedom to travel coast to coast. Golden Spike is a fitting location for manufacturing the rockets that today, like the trains of old, are opening up new commercial opportunities in space and will usher in an era where space travel is commonplace for would-be explorers. When the SRBs return, the casings and nozzles are cleaned, then insulated with a protective carbon-carbon material. The solid rocket fuel is created, and the boosters are reloaded. Occasionally, a fully loaded SRB would be fired to test design improvements or modification. The powerful rocket is secured horizontally and fired.
1, fire.
Several feet of sand is placed on the ground behind the rocket to protect the test stand. The blast is so hot that the sand is liquefied, and when it cools, it turns to glass. The temperature of the flame as it exits the nozzle is 5,600 degrees Fahrenheit, the same temperature as the sun's photosphere, the visible layer of the sun. When the rocket segments are fully loaded with fuel and ready to ship, NASA's mantra is, handle with care. An accident with a fully loaded rocket segment could be devastating. The SRBs are transported to Kennedy Space Center in Florida by rail from Utah. The trip is over 3,000 miles, taking the explosive rocket segments through or near numerous populated areas across the United States. After they arrive at KSC, the segments are joined together in the iconic Vehicle Assembly Building, or VAB, then mated to the external tank, which is attached to the orbiter, and the space shuttle is ready to launch. Just southwest of the VAB is NASA's Locomotive Maintenance Facility. Frequent maintenance and repair is performed to keep the mission-critical NASA train fleet in top condition. Chris Bryant takes care of the rail cars.
Our main job is to maintain all the rolling stock as far as the cars, locomotives, anything to do with the railroad. That's what our job is.
While Chris was working to replace a worn-out brake hose, he discovered a hidden problem that would forever change how NASA handles solid rocket motors.
The day that we were working, our job was to do the hoses. That was required, and that's what we were doing. And I was underneath hooking the hose, and it so happened to be where the center plate is. And my job by trade is a welder. So I'm always looking for cracks or anything, you know, just something out of the ordinary. Just happened to look up and seen the crack. When I did, I reported to my lead. At that point, we stopped everything. They knew that it was bad. I think it was out of about 63 or 64 inches of circumference in the weld, about 60, 61 inches was busted.
The center plate was hanging by a thread.
The magnitude of the crack was that of the 360 degrees around the center plate, the crack was 340 degrees. So there wasn't much holding it there.
The center plate is the main bearing point, contact point between the railroad car body and the trucks, the part that they actually roll on. There is no other feature. There's no redundancy in its safety. And by that single point failure, it was just a matter of time before they separated.
You would lose the solid rocket motor on a derail incident. Extremely concerning to the program.
NASA immediately stopped all trains and launched an emergency investigation.
The response was very quick. We had a lot of attention. They flew a bunch of people in, Alabama and the Marshall Flight Center, Houston. They had a lot of people here.
NASA awarded Chris for discovering the issue, but what he did not realize at the time is that he may have prevented one of the biggest disasters in NASA history. A broken weld puts a stop to all NASA trains.
We jacked up the cars and disassembled them so that everything that was involved could be inspected and x-rayed, and because first you had to determine what caused the problem before you could make a repair that was going to be worthwhile.
An investigation team simultaneously begins searching for the cause while inspecting all the rail cars in the fleet, hoping the issue is isolated to this one rail car. It was not.
We use 200-ton rail cars to move the segments. We have 24 of these cars in our fleet.
NASA is shocked to discover that out of the 24 rail cars, 22 had damaged welds. For years, the rail cars had been carrying fully loaded rocket segments across the United States. If any one of the 22 damaged welds had separated all the way, the resulting accident would have been catastrophic.
When they're underway, each car is close to 500,000 pounds each, and if you're moving at 50 miles an hour, that 500,000 pounds will travel quite a ways before it comes to a stop. So it could end up being a pretty good mess.
Extensive analysis and computer modeling was conducted to determine why the welds were breaking and why the problem had not been seen before. The same rail cars had been used since the beginning of the Space Shuttle program. For 20 years, the massive weight of the SRB segments created tremendous stress and strain on the center plate. Over years of use, the weld holding the center plate to the flatbed began to break, eventually leaving the volatile rocket segment hanging by a sliver of metal. If the final inch had broken, the center plate would have broken loose, the flatbed could have collapsed on the wheels, derailing the entire train and sending the fully loaded rocket segments tumbling out of control. The moment the fuel encountered an ignition source like fire or sparks, an unstoppable and uncontrollable chain reaction would begin, destroying the SRBs and everything around them. On their trip from Utah, the trains traveled through both small and large towns. Had the weld completely failed in a populated area, an uncontrollable fire and explosions could have caused widespread damage to buildings and homes, and possibly loss of life. The fuel is highly toxic as well, which would have required large-scale evacuations. According to the Federal Railroad Administration Office of Safety, there are approximately 850 train derailments each year. Many are minor, but some wreak destruction in their paths. Rail is still considered one of the safest and most cost-effective ways to transport goods across long distances. But when something goes wrong, the results can be devastating. The last tiny inch of the weld holding the center plate in place and one technician's timely discovery had prevented a possible program-ending accident that could have been second only to the loss of Columbia and Challenger. With the entire NASA train system shut down, new solid rocket boosters are now stranded in Utah. But an aggressive launch schedule is demanding a constant fresh supply of the rockets. If NASA cannot fix the problem soon, millions of dollars would be lost in mission delays. This space mistake is a chilling reminder that the dangers of space exploration are not only restricted to launches, landings, and on-orbit mission objectives. The manufacturing, transport, and processing of the highly explosive fuels and motors, which in many ways are the heart of space exploration, are just as critical. For over 20 years, the rail cars were used to transport the rocket segments, but the center plate had never been inspected in all those years.
Years ago when these cars were built, we used different standards for our safety factors and stuff, and these cars being very heavy caused fatigue. The acceleration of the fatigue was more than anticipated. And it should have been caught sooner, but using the old guidelines, they were within the normal range of the old guidelines, but we just found out that our inspections have to be more frequent and a little bit more intense.
NASA initiated an aggressive repair schedule to fix the broken welds. To reduce the strain on the center plate and slow down the degradation of the welds, NASA lowered the speed limit of the trains transporting fully loaded segments. NASA also implemented regular inspections of the welds. Solutions that will all lead to the flight schedule being met and a successful controlled process of transporting the segments.
We need to have a good inspection criteria. We need to have a good repair criteria. And once that's established, which we believe we have, we need to make certain that we don't drift from that.
Today, solid rocket motors for the new generation of spacecraft are still being shipped from Utah and other places across the country by rail. NASA learned from their mistake and fixed the problem. Each previous generation of spacecraft provides a wealth of knowledge and experience to further exploration. As NASA focuses on placing humans on Mars, new challenges await. Many improvements will not even be discovered until something goes wrong, because space exploration is fueled by the unknown. No one can fully predict how the harsh environment of Mars may affect people or hardware, which is one reason we must go there. The astronauts, technicians, and engineers who have dedicated themselves to exploring space will never let mistakes stop them. They innovate, fix the problems, and ultimately become better to go further and discover more. Thank you.